Hello everyone and welcome to Driving Conf, the learning journey. My name is Aleksov and I've been writing software on a daily basis for the last 15 years and I would really like to share with you some of my experience. Back2Basics is a new series that I have recently started, which goes back to the very primitives of software development. Nothing guarantees for success more than a strong foundation. For the experienced amongst you, this might be a good refresher, and for those of you who are just starting your careers, I hope that you are as surprised as I was when discovering these topics. We'll start with binaries and interoperability, and hopefully we'll end up with a full-blown application capable of displaying beautiful graphics, playing high-resolution audio, and all of that on the most popular operating systems out there. Along the way, we might also break some myths, and we should have fun doing that. Okay, as usual, before we start, a very quick disclaimer that the opinions expressed in this talk are my personal ones. They don't express my employer's views on these subjects. I know the trademarks are obviously used for illustrative purposes. I'm not here to cover things like, some theoretical aspects of computer science. I'm actually here to try all the animations in Keynote. And also that includes not covering data structures and algorithms, which are valuable and they do help you, but only if you understand the problems that are being solved. So this talk will be very, very practical with actual concrete examples. And the starting point is understanding your hardware and also understanding your operating systems. So there are just we're not obviously going to cover everything, but just the most important parts with actual examples. So you do need to know how your hardware is laid out and what are the properties of the machine where your software is going to run. And if you don't, you do need to write some code that is going to test for that and actually try to figure out what would be the best execution model. So this image does not reflect, obviously, all hardware architectures. It's here for illustrative purposes. But we have more than one core most of the time. They do have some registers. I've only put RAX here as a reference, which is the 64-bit version of the register. EAX is the 32-bit version of this register. AX16, AH is the higher 8 bits of that, and AL is the lower 8 bits of that. So this is how Intel managed to maintain backwards compatibility of its software, just building on top of the 8-bit register, A register. In the in the x86 architecture, and this register would be present on every core. Most of the time there would be a level 1 cache for every core. Sometimes they do share it, so this is very important, but the most recent processors have a dedicated L1 cache per core. Before that, there is a prefetch, a fetch, and execute cycle, which is very important. It also contains a branch predictor, and I'll explain why just in a second. And once you have a cache miss, you go up to the level 2 cache. If you have a cache miss, you go to the level 3 cache. RAM, if the data is not present in RAM, I'm pretty sure you've seen that. But it's we go and fetch it from other external devices. But the point here is, generally, as a rule of thumb, one level up takes you an order of magnitude more in terms of time. So if the data is not present in the level 1 cache, you'll go to the level 2 cache, which will take 10 times longer. If it's not present there, and in the L3 cache, you go to RAM, that's 10 times more. So now you're doing 100 times slower software. If it's not present in RAM, or you want to copy it from somewhere else, like PCIe, that would be 10 times slower than that. And we are 1,000 times slower. SSDs, HDD, finally going over the network, would be 1 million times slower to retrieve a predetermined set of data. How much data is what cache lines are important for. So you need to make sure that generally when you retrieve data, you do it as per your cache line size. You don't want to make cores conflict with each other. So one core preempting or evacuating the cache of that's being used by the other core. So you can really misuse multi-threading in that sense. The branch predictor. So if you write code that's not predictable, for example, you consume random values, right? That's not predictable. And you have a misprediction in your branch predictor, it would take many cycles to clean up everything that has been prefetched, put in cache, and to re-execute all over again on the right branch of the code. With that said, finally, just a couple of more things. Programming on the stack is much faster because it's direct. Many times the offsets can be computed, and consuming using the heap, so dynamic memory, involves indirection, right? So you don't know the address of what you would like to execute. Most of the time you do need to fetch or compute the address or allocate some memory in order to use it. So it's not working well with our pipeline. Also, as a small comment, class-oriented programming does not really play nicely in this kind of hardware setup that we have here, because all of a sudden, if you don't take extreme care to properly organize and allocate your classes, all of a sudden you're jumping all over the place, consuming things from RAM, cache misses all the time, and so on and so forth. Lastly, the floating point arithmetic unit could be shared between cores, or could even not be present in some of the cores. So that will generally lock your program or your software to a specific core, or it would make the core wait until the floating point unit is free to be used again. The operating system. So you do need to know what are the capabilities exposed. So that would be Windows 32, 64 APIs, and POSIX. You do want to know generally at a high level how the scheduling is performed and when your program could be interrupted and offloaded for some other program to execute. And it's also important to know the performance of system calls that you perform and how long they would take. Nowadays, non-blocking approaches are preferable, so these OSs do expose some mechanisms to do that. On Unix, you have KQE, on Linux, you have EPOL, completion ports for Windows, and some of them do expose direct access API because these system calls are generally slow. You don't want to use them for some, and they can offload the program and they can raise some interrupts to be handled additionally. Related to what we said previously about evicting cache and so on and so forth, OSs do expose some direct APIs for some of the most performance critical hardware out there, but nowadays almost everything is performance critical, I guess. So it's good that we're seeing more and more of these direct memory mapped APIs out there. Today, as I said, we're going to cover concrete examples, and we'll start with binaries and interoperability. So covering executables on different operating systems. So executables are really like every single thing that executes on the machine. It's either source code that has been tokenized, parsed. The result of that is an abstract syntax tree. It has been then translated into bytecode or bit code, and then translated into actual assembly instructions, linked with some other assembly, and encoded for a specific architecture. You can start probably at any single point of this bullet list, essentially, but at the end of the day, you're always going to compile to some assembly for that particular hardware architecture and OS pair. And executable just export an interface of how they should be loaded in the operating system. That's generally a main symbol, or as you already guessed, it's the main function. So symbols and functions are kind of, well, you can have symbols that are not functions, but symbols and functions are kind of synonymous in this context. On macOS, the executable format is macO. On Linux and Music, it's either elf or a.out, which are also very similar. And for Windows, we have portable executables, and libraries, they're executables without the main function, essentially. So they do have multiple global symbols. We can have code libraries, really many varieties: bytecode, bitcode libraries, shared libraries, static libraries. Now, depending on the compiler, you could have bytecode and bitcode libraries, which is an intermediate stage of compiling your software. And some wouldn't expose those. And shared libraries are, so for a lot of time there has been a discussion between whether to use shared libraries and static libraries, and people have been always leaning towards using shared libraries. But it's kind of funny because all the problems that we have by using shared libraries kind of get solved by using static libraries. And I see there's a small typo out there. So we are kind of reevaluating those choices, and a lot of the software nowadays can be built by using static libraries. And I can remember doing that on actual production software and getting laughed at for using static libraries. So it's nice to see that there's some out-of-the-box reasoning. So the advantages of static libraries is that because you're essentially not linking the software and optimizing it during build time, but you're essentially shipping all the instructions as they were when compiled without being linked. At the point of linking to an actual executable, you can perform much more optimizations. So we can see what actual functionality is not being used, and we can cut it away. We can calculate offsets, calculate some addresses. So much more optimizations from the compiler. And Linux historically has been having this problem where every single distro would have a different place to put the shared libraries and to look them up, and they would have different versions, especially some of the core runtimes. So that's why you don't have portable Linux software. I hope I said Linux. So you would get an executable for Linux, try to run it, and it wouldn't find a library, and it will crash. So I'll give you some examples of those kind of errors and how to solve them as well, because once you understand that, it's rather trivial to solve these issues. So about the formats, and they're not really issues, right? They are actually useful errors. About the formats, we have on macOS, we have shared libraries or dynamic libraries, which are kind of interchangeable. We have dlib and .so. On Linux and Unixes, it's .so, and I'm sure that you saw DLLs on Windows at some point or another. Static libraries are in the format of .a for POSIX systems like macOS, Linux, and Unix, and .lib for Windows. And there are environment variables that you can change on every system to point it to the right place to load these libraries. So there are different ways to link into those libraries. You can do that implicitly during compile time by putting some metadata and some placeholders in your executable that you need a specific library to be loaded. And that is the implicit way. And you can explicitly actually load the library during runtime by using mechanisms such as dopen, and you can look into symbols or functions into those libraries using dosim. And for Windows, the counterpart would be load library x and get proc address. So with that knowledge, we actually have a very powerful tool at our hands. It means that we can now start treating programs as data, and we can load them, offload them, manipulate them, change them, do whatever we want, because at the end of the day, they all have a common interface, and they are all instructions that we can interpret or change. So we can start manipulating the existing software instead of being, and have more control over it instead of being afraid. Compilers and linkers, well, you should know the most popular ones, the most used ones. So LLVM is apparently being preferred for building general purpose software. The GNU compiler collection is the one that's preferred in Linux environments. MSVC is the Microsoft compiler, so the one that's now shipped with, the runtime that's now present with Windows 10. And if you want to do POSIX software on Windows, you would need some kind of intermediate cross compiler like MinGW that can emulate the POSIX system API. If we summarize how modern software looks like, we would kind of have a very similar diagram. So we would have an API of the operating system. For Mac, that would be a Cocoa API or the POSIX standard, which is also supported for the most part by Linux and other Unixes, but there is some specific Linux functionality exposed by the Linux API, which is not part of the POSIX standard, as we saw earlier. Things like EPOL, so asynchronous file descriptors and efficiently notifying them. For Windows, we have Windows.h or the Windows 32 or Windows 64 API, which are the same thing. These words are kind of used interchangeably depending on, or flags during compile time, depending on which kind of architecture you're programming for. On top of those, we generally have some kind of libc or some kind of C or C++ API, Objective-C runtimes, MSys2 if you're running POSIX software on Windows. And on top of those runtimes, we started building some interesting libraries like libjvm for the Java virtual machine, hostfxr, which enables us to host a .NET runtime and run our C# applications, .NET applications. V8, but it could be any other JavaScript compiler and runtime to run our JavaScript files. And Python, also known as the best wrapper of C, is available in libpython, and it runs our Python files. But these are all standing on the shoulders of some of the giants out there, like libcrypto, libSSL, libboost, which not many people like actually, but it is used in a lot of software, out there. GL to run our graphics, Vulkan, sorry for the typo there, DirectX, zlib for compression is all over the place, and SDL for multimedia, and so on and so forth. So without further ado, let's jump to the demos, write some code, compile some executables on different operating systems, compile some libraries, link them together, and see how we can also have some interoperability in place between the different runtimes. So we'll start with Hello World applications. Here's an executable that just prints Hello World, but it also has some garbage in it. So it has 8 megabytes of data. So we are going to compile that using CLang. And most compile, so CLang, GCC, MinGW, which is again an interface on top of those, they would kind of have the same interface. So what we need to tell them is what is the level of what we are telling them, not this is an optional flag, but don't perform any kind of optimizations, so O0, and we want you to output into this directory the executable, which you're going to create by compiling this unit of code, which is our hello world.c. So if we run this script, we'll get an executable in our macOS folder. Surprise, surprise. But a few things to notice: if I run the file command, which will output some information for this executable, we can see that this is a Mac-O 64-bit executable. And if I run O2, I think it was the L flag, it would essentially tell me that this is linked against libsystem, which is the standard library that macOS provides. And we can also ask the compiler to produce just assembly instead of linking the file and converting it into bitcode. So if we do that, it will produce this .s file. So I won't make you read assembly code, but I want you just to spot, which is actually quite easy as long as you don't need to do all the offset calculations. But a few things to notice: we have our data here at 8 megabytes of data initialized to 0, and the first byte is A, because this is what we asked to our compiler to do by typing that global variable. So you see, it didn't by default optimize it away. We told the compiler not to optimize. We have a get greeting message, which is again a global. And we have our main method somewhere here, which is as well global. And finally, we can see that we have a printf call, which is something that the operating system handles. And we should be putting our result in AEX. So we are returning 0 from this call. We can also ask the compiler to produce bytecode by setting dash or some intermediate representation by setting emit VM, and most compilers would show you either an abstract syntax tree of what they have so far in the compilation, or in case of hello VM, this LL file, which I have created in advance, but I just run this. So here you see we have this intermediate between assembly instructions with some offsets and sizes in place, but also at the same time we have the concepts of function printed in a visible text. So it's always nice to examine what the compiler is going to output for some specific compilation units. Finally, we can ask the compiler not to link the application, so we can just produce an object, and we do that by passing the C flag. This will be a binary object, but it can be linked against by other programs. So this is the .o file, and see it's a micro 64-bit object. We can do the same for Windows. So we do need to install MinGW and MSys2, and right after we do that, we should have a MinGW terminal available. So I'll just navigate to the demo code. Okay, and let me launch Visual Studio Code quickly. Okay, so in the case of MinGW, we will use the GCC compiler, which is available from this environment. And everything else is pretty much the same. So this is actually going to produce an portable executable file for Windows that we can run. And it's properly linked, so we don't need to worry. It's probably not this one. Okay. If I now go with, maybe let's use some other application. So I use command prompt. See, now we have the hello world MinGW executable, and surprise, surprise, it does the same thing. Finally, we can use the MSVC compiler that comes with Visual Studio if we select the C and C++ applications in the install, so that would be available from the developer prompt. So here we're going to run cl.exe, tell it to compile our same source file, hello-world.c. And if you want to tell it the output path, we need to pass the /fe parameter, and this will build our hello world without the prefix. So let's do that. So you see our files are here, properly compiled, and if we wanted to run that, we can say Win64, which is our output path, hello world. Okay, so we use the same source code file to compile it against 3 platforms. Let's do Linux, just for the sake of completeness, but you can expect that nothing major changes in there. What I will compile in Linux is the following. So we run GCC with basically the exact same parameters that we use in MinGW and also clang, and tell it to output to the Linux 64 folder inside bin. And we can also ask what kind of file is this. And you see it's a 64-bit ELF executable. And we can also ask MinGW because it has the file utility. Otherwise, you can use file command version for Windows, which also works. We're going to ask what is the type of the Windows executables. So let's do hello-world.exe. So it's a portable executable. And we can also, 32-bit by the way, and we can also do hello world MinGW portable executable plus, which I think was done to host the 64-bit versions. Okay, let's do some libraries. Back on the OS X machine, what I've done is that we are going to compile greetings-it.c, which is essentially just a library that has two methods: get greetings message, get exit message, and it has some garbage. I actually forgot to show you the file sizes, so this was very, very important. Of the final executables. So if we see for macOS, the file size is 8 megabytes. And that would be the same here. So the compiler did not optimize absolutely anything in our case. Both the Windows one and MinGW, and it's pretty much the same for Linux. Okay, so we'll do some optimizations later as well. Let's do libraries quickly. So again, I've purposely put some 8 megabyte garbage in the general purpose library that we won't use, but what we will use from this library is get greeting message. This time hello world in this library is in Italian, that's why the -it, and there's also a Bulgarian version of the library that has hello world in Bulgarian. But they do keep the same interface. So the interface is defined in the header file, which is generally inside the include directory. And we expose all these functions externally. The additional code is done for Windows because we need to put an export signature for the Microsoft toolchain. And if we compile this, so we'll use the 00 compile library it, but I think you saw the script. So it's going to call the CLang compiler, pass the dynamic lib flag, or for Linux this is -shared. We need to point it to our include directory, so where the headers are defined, so that when we actually compile the greetings-it compilation unit, it will look into the header folder and the includes folder, and it will find that specific header, and we say that we want to output this library in our lib64 folder. There is no official convention for this, but this is being followed for 64-bit applications now, apparently. Okay, and if we check you can see that this is a Mac O 64-bit dynamically linked shared library, and with auto we can see that it also links against libsystem for macOS. Another POSIX utility is nm, so we can do nm-g and our library. And nm can actually show us the symbols being exported by a particular collection of executables. So we see here we export our buffer, which means that we are preserving the 8 megabyte size of garbage. We are exporting our exit message, and we are exporting our get greetings message. Okay, now how do we build a static library? Well, the process is fairly similar, but we don't need to link it, remember. So we call our compiler, we pass the O2 flag, just to make sure that we run some basic optimizations. We enable link time optimizations. Some compilers need to do that while building the static library so that these optimizations can work when the library is linked. Others don't. I'm not particularly sure about CLang on OS X, but it appears that I need to enable the LTO flag when I build the static library. Again, the library source code itself includes its header. So we need to include that in our we need to include the folder in our build script, and then we want to indicate to the compiler not to make the addressing portable and not to use absolute addresses. With that, we then create an archive of the object file, and we put it in a different library than our shared one. If a shared library and a static library are in the same folder, when you try to link to them, most compilers will generally prefer the shared library. So let's go ahead and do that. By the way, don't worry about this warning attribute unknown error. This is an attribute that we've put into the source code for a different toolchain. So if we look into our static folder, we can see that we have the Italian library compiled. Previously, I've compiled the Bulgarian Hello World library as well, but we can do that again. The only thing that changes, of course, is the compilation unit. So instead of compiling the -it source code, we compile the -bg. And we can also compile our shared library in Bulgarian, which is this script right here. Again, dynamic for macOS, shared for other operating systems. I'm not going to run this demo on Linux, Windows, and MinGW for Windows, but all the source code files are here, and I'll share them with you. So if you want to play with this on your operating system, if it's different from Mac, you can just download the source code and try this for yourself. Again, as you saw, not much changes. Generally, we use a different compiler. Dynamic, like some of the flags have a different name, but most of the time we tell the compiler exactly the same things: how much to optimize, where to find headers, which files to compile, and what the output needs to be. Okay, so let's have a peek in our lib64 macOS folder. We have our 8 megabyte static libraries, and in our static folder, nothing should have changed so far. So there are our static libraries as well. So on Linux, this would be a .so. On Windows, this would be a .dll, and on Linux, this would remain .a. And on Windows, this becomes a .lib file. But the purpose of these is all the same, and we can link to them with different levels of optimization, as I already said. So you can play with these files. I've also included Linux in the most recent version, which is basically the same as in OS X almost, so not much changes. Again, POSIX systems are very similar, so most of the time the issue is between source code that should run on Windows and source code that should run on POSIX. So let's actually start using our libraries. For that purpose, we need to link into them. So first of all, I have a script that doesn't work. So we're going to call our compiler with an executable source code file. So we have a main. We want to call the get greeting message from our library. We have included the header in the source code, and we still have some garbage to optimize away. But if I call the script, I think it was 00. I'm in the wrong folder, of course. So this is a very typical error. So some file .h was not found. Well, what this means is that in our compilation script, of all the directories we needed to include, we didn't include the one that contains this particular header file. In our example, we didn't include any directory. So we need to fix our script a little bit and pass the I flag to include the directory where our header file greetings.h is located. Another very common error of course, that's the wrong script, is that once we compile during the linkage, we get this undefined symbols for architecture, blah, 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 the architecture you're compiling for, which symbol was not found and where it was referenced from. So what it says here is that in our main method of the hello world object, we are trying to use a get greeting message, but that was not found. So generally, these kinds of errors are because we didn't tell the compiler where to find the library where this particular symbol was implemented. And the way we do that is by passing the -L capital. So you see a small pattern here. Whenever we need to point to directories, we pass a capital I for includes, L for libraries. So we point our compiler to a folder that contains the static library in this case. And then we say, we want you to link greetings-it. Now there is a convention here. When we pass the library, it automatically searches for files that have the lib prefix, and then for the platform, the appropriate extension. So in this case, it would be dlib. So this is a convention because when we try to compile on other operating systems, we don't need to change our compilation scripts to look for a particular platform extension. So we link to the greetings-it library, and as you saw, I erroneously ran the script earlier. It actually compiled, and it put the output into bin macOS hello world. Now, what happens if we try to run this file? Another interesting error that we very often get is library not loaded. So we did compile our executable successfully, but then it was unable during loading to find our lib greetings-it.dlib. And that's generally because we didn't tell the operating system when we try to load the file where to seek for our library. Now, different operating systems would look in different places, but as I showed you earlier, an easy way to do that is to either include the library in the folder where it's looking for. So in this case, it's looking into lib64 macOS lib greetings-it, and we don't have the library there, so we can just copy it. And we'll copy this into our local lib64 folder, or we can just link to it, of course. But if I run the script now, we get a hello world message. A different way, so let me clean it again and try to run. We get an error. Is on macOS to pass this environment variable, which tells the operating systems in which folders to look for libraries. So we'll say DOD library path as an environment variable equals this, and we will actually point it into our one libraries lib6 folder, the main folder, and then we will execute our binary again. And it's actually looking into the root, so we need to say lib64 macOS. This is where our library is, and it runs. Now, an interesting thing is that if the same program, our hello world, links to our Bulgarian library, because it has the same signature. Remember, the only thing that connects these codes together is basically signatures. So get greeting message can be called from one assembly or from another, from one library or another. We can essentially compile our code to link against the Bulgarian library, and all of a sudden we start outputting messages in Bulgarian. So I'll call .03, which is going to compile our source code, but this time link against greetings-bg. And if I run it, I'll most probably get an error because I don't have the file here. I don't have the library in that folder. So you see, so Linux is constantly hitting errors like this because there is no convention on no single way and convention of where to put libraries, when to look for them, and also, well, there are some, but they're not respected across the different distributions. And also there will be different versions. So maybe there is a version of our library which does not have the get greeting message. So they would be binary, they would be incompatible on the binary level. I'll just pass the same DOD library path. For Linux, this is LD library path, and for Windows, it just looks into your path system variable. Oops, I did the same error again. lib64 macOS. There we go. Now, one thing I want you to notice, well, let's link with the static library. So this is exactly the same, but we just point our compiler to the static version of our library this time. And we're going to optimize with some flags, especially link time optimization. And I want you to notice something. So this is the 0-7 script. And I already do have a bunch of binaries in this folder, but look what we have now. So the Bulgarian executable we compiled, the hello world in Bulgarian executable, is 8 megabits. But what does this do? So we didn't optimize away the garbage. And additionally, it's going to load the BG library, which has another 8 megabits of garbage inside, and this would be 16 megabits of non-optimized code sitting here. Now, if we enable the optimization flags, it can actually see that our hello world code here does not use this data storage, data variable, and it can optimize it away. So it suddenly becomes 49 kilobytes, but this is still going to load our shared library because it's shared, that one was not optimized. So if we actually look into our libraries folder, you see our shared libraries were not optimized because they are general purpose. The compiler doesn't know whether we are using that particular data, that particular variable or not. So we've managed to halve the size, so we're actually running at 8 megabits now. But this is not memory that we are using productively in any way. And with the static library, because we passed some link time optimization flags, and here we're not going to load libraries from anywhere. The greetings-bg code has been incorporated into our statically linked executable. Our total size is 50 kilobytes. So we now have an executable that can use 50 kilobytes of memory, and we have one that can actually use 8 megabytes. So you decide which one is more efficient. And of course, the added advantage of statically linked executables is that they don't have any of these looking for libraries plague, because the code is already part of the executable. All the library code is already a part of the executable. Of course, they do have these advantages, but in terms of optimizations, there's no better way than this, probably, if we're looking to reduce the amount of, and also to make sure that our binary is going to run on any system. We've tried fighting this problem with many interesting other ways, like running things into containers, downloading all the possible dependencies every time in a container image. We try to run an executable just to make sure that it runs properly. Meanwhile, you just statically linked an executable and you're good to go. And I'm probably going to get a lot of critique and backlash for this, but that's just the reality. So more efficient executables because they can be link type optimized, and they're not plagued by dependencies all over the places. So another interesting compilation target is this one, WASI and WebAssembly. So you see, we still need to build our library for different operating systems. And what WASI defines is, it defines a common runtime. That's not the Windows one, it's not the Mac OS one, it's the WASI one, it's the cross-platform one. And we can build targeting this runtime. So if we download the WASI SDK, so that's basically the same approach of WebAssembly, right? We enable a system interface across the web. If we use their compiler, we can actually compile our libraries. There is still no format for static libraries or shared libraries, so we can only output like objects now that we can use to link later in our executables. And this is what that attribute that other compilers didn't recognize is for, because our libraries now wouldn't have an entry point. The only way to make sure that these symbols are preserved and compiled is to put some attributes on the methods. I'm speaking a bit vaguely, but I'm referring to this attribute here. So this is used for our WebAssembly compilation. And we're essentially telling what export name to use, but we're doing that so that the compiler would preserve our symbol. And we can also do an executable. So optimize, link time optimizations, pretty much the same flags that we use, but this time the output is .wasm. And if we run that, by the way, I'm just running this again to make sure that something didn't change in the meantime, but you'll see that I've run them in the past. So now we have our hello world wasm that was optimized. All the garbage was removed also from the greetings BG and greetings ET libraries. And we can use different ways now to run this program, but one of them is wasm time, which implements the wasm system interface. So it can pretty much load our hello world wasm, and there we go. And these outputs are totally usable by WebAssembly. So now we use our single code base to run across how much, like 5 different platforms, but it gets even better. So let's, you see that specifying every time the compiler and the flags isn't really fun, especially having like, how much, like 12, 13 different scripts to run. Of course, we can wrap all this into one script for all the different platforms, but it's just painful. So one of the solutions for this is make files, make as a program. You've probably seen it elsewhere. And this is just an easy way to specify what compiler we're using. But these are environment variables, by the way, so we can also use these environment variables without make. So we can generally tell what compiler we would like to use, what flags, what linking flags, and where the output needs to be. But makes it easy to resolve dependencies. So we can say that we want to compile hello world. We can say what dependency it has. So make will automatically find these dependencies, and it will compile them if we tell make how to compile those. So in this case, we're saying you need to compile the .o object of hello world. This is how you compile it, by using that compiler with those flags. And finally, you need to link it, and you need to put the output here. So it's a more clever way to do those shell scripts and configurations. And we can do also some checks. So if we are running on Windows, we actually want to pass some other flags that are specific to Windows. If we are running on Windows on MinGW, we want to do those instead, maybe change our outputs, change our flags. So I'll run that very quickly, but the idea here was that you will encounter these make files very often, and you shouldn't be afraid of them. So just run make in the folder. It will run the default target, which is in this case is hello world. And there we go. We have our output. Great. CMake is another one, which is a little bit more evolved. So with CMake, we kind of do the same. So we set some compiler flags. We can say what we want to produce. So in this case, we're working on a project that's called Hello World. We want it to have an executable, which is built using this source code from our previous folder. We also want to link to a library, which is the greetings library, and it's going to be static, and we tell CMake how to import that. At the end, we want to link Hello World to the greetings library. So you see, it's a little bit of a higher level way to do that. The way we use it is that generally the convention is that we have a build folder. And in this build folder, we run CMake from the previous level. So our CMake lists file is here. And it's going to essentially configure our program and produce a make file in our build directory, because this is the default generator. By default, it's going to produce a make file. And if we run this make file, our program will compile link. So you see, it's a little bit more elegant way. The nice thing about CMake is that it can produce Ninja build files, which is a different build system heavily used by Google and other C++ projects, but it can also produce Visual Studio files. So Visual Studio solutions and projects that can be compiled from our same code base. And to do that, we need to pass G. So we are saying, CMake, I want you to use the Visual Studio generator, this particular version, and in our build folder, we have a Visual Studio solution. So this is all nice and great, but we don't want to write all of our source code in C and C++. we want the pieces that need to be fast to be in C and C++ or C++. But most of the time, we really just want to write our Java, C#, JS, Python. At least these are my favorite languages. So I'll show you a way, of course, on the browser as well. I'll show you a way to essentially do the same, whether implicitly or explicitly, by using your favorite managed language. So in C#, the way you call into these static libraries is by using the DLL import attribute, which essentially does a DL open or a load library on Windows, and a DSIM or a get proc address on Windows to essentially load the static library, and then we can call into it. So we declare it as a static external, and we do need to do some marshalling. So every time we move data from one language to another, from one convention set to another, we need to do some marshalling of the language. So of the data, sorry. Let me show you that very quickly. I'll do a .NET run. Oh, let's rebuild just in case. .build. And we can do a .NET run. Now you see what we are going to run here is our write line, and it's going to print our greetings, get greetings message from our library. There we go. If we load a different library, it will be the same. So we're just loading another piece of data that's also executable, then we know how to interpret it. And when we go through the operating system, it actually marks which regions of the data are actually executable, right? Then we can do the same in Java. So for Java, the process is a little bit more involved. There are some headers, but let's say we have a simple Java program that print lines a native method, a result from a native method. In this case, we're going to call this native because we need to provide some glue code for Java to be able to marshal the data. There is no automatic way in which it can marshal the data. There are some other libraries like Swig that we can use to generate that glue code, but it really depends on how you would like to do that. And then we need to statically call once, when we load the program, we need to call load library and give a reference to our glue code. So this is not the actual BG or it library that we have. This is a glue code library. And we need to implement that glue code library ourselves. Now, I think it was javac -h that can produce an automated header for the glue code. So let me see that very quickly. So we can do javac-h. It will generate the header in this folder, program.java. And we have our header here. And we need to implement it. So we can create a small C program that includes our, remember this is the glue code. So we're going to link into our greetings header signature. Then when we build this code, we're going to link into the library. And into the glue code, we need to say what happens. So essentially, we're going to return a new UTF string, and that will be coming from get greetings message from our shared library. This is all the glue code we need to provide. And we need to compile it. So in order to compile this, here I use GCC, but you can use any other compiler. We need to point it. One of the includes, as you saw, is, sorry, not here, but here is jni.h. So we need to include the folder where jni.h is located. It's in the Java home include directory. Then we need to include some platform specific. So the Darwin includes in the Java home. We're going to output our static shared library here. That's shared, remember. And we're going to build our program.c finally, linking into our greetings-bg library. So if we do that, there is no greetings. I probably moved folders. So let's see. Yeah, I moved this one folder up, so this should be like this. And I probably need to change the library folder. Okay, so now, well, we did build. So now we need to run our Java program and see if it works. So remember, in our main, we're just printing get native, which is going to call our glue code and get from our library the greeting message. There we go. Calling into native code. So now let's do Node.js as well. For Node.js, we have, and V8, we have Jeep as a build system, very similar to Make and CMake. More like CMake because it produces build scripts. So here we say we want to build a greetings module. This is where our headers are, and I want you to link into our greetings-it library, and the source code to compile is greetings.cc. Some marshalling involved here as well, so we do need to provide some V8 glue code. Essentially, what will be exported, and this is also the initialize method that sets what messages would be visible to JavaScript. In this case, it's what methods would be visible to JavaScript. In this case, it's the get greetings message, and it's implemented by the method function. This is V8 specific, but essentially getting us a sandbox where we can call our get greetings message, put the result into the return arguments of this call. Then once it gets compiled, which will probably go here, but let us do that quickly. So you see, Jeep actually generates make files. Let's see if I remember the syntax. It should be node Jeep configure. I think I changed my Node.js version here, so probably I need to change this back to something else. But if it works, it's going to build our greetings.o object. So you see, we get this error where we're actually using. So this is where all the shared libraries errors again manifest. Like we're using some libraries that were built for 10.13, but now we're building on 12.0. Essentially, this is the Node.js version that we're using. So if we switch to a newer version, but it's very difficult to pinpoint an exact version where you wouldn't get warning messages. And then we can just run our program.js. Ciao mondo. What we do here is just require a build the Node.js executable file that was in the just built by Node.js in our build release folder. So the script that we generated using Node.js, very similar to CMake, generated some make files, which we can also run manually. And the output is actually here. If I remember correctly, this is a binary file, so it cannot be opened. A library that then gets loaded by the Node.js runtime. Same with Python. So Python, because it's so close to C, it doesn't have much marshalling that needs to be done. It just needs to be informed on what kind of types we are going to move back and forward. So we can use the C types module to load our greetings BG, and depending on the platform, this will either load again using the methods that we saw, the open and dsim for POSIX, or it will use load library and get proc address for Windows. Our function does not have any return types, any return values. It's a void function. Does not accept any arguments. It's a void function for the input, and as a return we get a pointer to character bytes. And if we run it, we get our string back. Using buffer right here because our output is UTF-8 and this supports UTF-8. It actually just writes to the console which supports UTF-8. Finally, WebAssembly. I just took the libraries we compiled earlier, and we have some JavaScript code to load the Italian library and the Bulgarian library as WASM modules. We go into the get greetings message. We actually get a pointer. Remember, everything is addresses in memory, so we get the offset in memory where our message begins. And then we need to convert that string from memory at the offset into something that's usable by JavaScript. The way we do that is characters in C and are not terminated. So when the string ends, there is basically a 0. That's how there's a 0 byte. So we just walk through the array and we count our length. And this is where we get the length of the message, and then we can say, okay, at this offset, take this amount of bytes, and we use take decoder to translate them into UTF-8, interpret them as UTF-8. So I can run, if I'm again on the right Node.js version, I should be able to run on HTTP server, and I'm not, because I probably deleted it. Let's see if Async has it. Yeah, so I ran on the wrong directory. Should be WebAssembly. And we print ciao mondo and zdrowie to the console. Okay. Now, with all this knowledge, we can do even more interesting things. So we can actually write a runtime that loads the common language runtime, that loads the Python runtime, that loads the JVM, it loads V8. And we can use then higher level languages as scripting tools to provide some programmability over our C and C++ implementations. So I've written the code to essentially load JVM, load Python, load JS, V8 in this case, and to load COR. We can have a look at it. And then I defined a convention of how I would like to provide some programmability. In this case, it's a very simple thing. We ask our plugins to implement a tick method, and we're going to call that tick method with some string. Of course, this is a very simple interface just to prove the idea of how it might work, and then you would like to have something more sophisticated to provide more programmability over your runtime. And for JS is the same, so it's a tick method. For .NET, I actually have them in a separate folder. So you just have a static class with a static tick method. Remember, we need to do some marshalling here. And for our Java, we don't need to do much. Again, it's a static method. And we print. Now, going into... So we provide very simple interfaces like load COR, tick COR for our tick functionality that we want to call recurrently. The same here, so tick.js, load.js. Forgot that I implemented the JVM as a header file, but the JVM loading as a header file, but for Python, you can say tick Python, load Python. And I wouldn't necessarily go into the implementation of these, but they kind of do the same thing. So they locate the Python initialization procedures, call them so that the Python the runtime of reference, in this case Python, is initialized properly, and then we look for a tick function in our source code. We get the address of that, so this is generally an address somewhere in memory that we want to call, and every time we want to call tick, we essentially marshal our native data into something that Python understands. We call the function with that, and we need to make sure our memory is freed back. Java, more or less the same. Bootstrap the JVM, we find our plugin class, we find our tick method, and when we need to call the tick from our runtime, we marshal the data, call a static void method using JNI. and we want to make sure that, again, memory is freed right after we are done. We can do also more sophisticated memory management, but this is just enough. For JavaScript, we need to load the V8 runtime, linking it to lib platform and V8. You can forget about this. It's just a custom console implementation that we then expose to JavaScript, but the idea is that it wouldn't buffer, it wouldn't flush the output buffers once we log, because I wanted to do some benchmarking later. And in our tick.js method, we need to respect some V8 calling convention. So we need to acquire a handle, we need to acquire our local context for this scope, we need to marshal our arguments, and finally go into our function, again tick, and we got the reference from that earlier in the code when we loaded actually V8. So see, we actually load our JavaScript file as a string and compile it with V8, and this is where we acquire this is where we acquire a reference to our tick function. And for COR, it's a little bit more involved, but again, because we have the headers, I'm just using some code from Microsoft here. We know when to look into the hostfxr library to be able to load a COR host the right way. So I've hard-coded some paths here, but this is essentially where I have my .NET version installed, and we can, just to show you the explicit way of loading these libraries. So on Windows, we call load library and get proc address. On POSIX systems, we call DL open and DL sim to look in for the address of a particular function that we're interested in. And this is how we can dynamically load and unload and extend our code base and our runtimes. And here it's more or less the same. So we do get a function pointer into a particular method of our .NET type. So this is the type that we want in this case, driving plugin and the tick method. So quite involved, but again, this provides so much functionality to our application and some nice scripting on top. So really nice to have such extensibility of the application. I'll jump into our runtime. So the way we compile this is that there is some C++ involved, which is the choice. Sorry for that. The choice for V8 is to write it in C++, and for COR as well, or at least to have the interfaces like that. So the easiest thing that we can do, instead of fighting the decision of the developers of those libraries and trying to load it into C, to compile it with C or something like that, or load it with C, it's just easier to use C++ in this case. And here we don't link into anything, because for COR we actually do a dynamic lookup during runtime, so we don't need to link into .NET or something like that. We're going to load that by loading a library from the disk explicitly. The same is for, so we're going to output this as our own library called libcor. So this is something that we built. And then we can have a lib.js build in a very similar way. In this case, I'm pointing into my local build of V8. I really hope I didn't delete that for the demo. Yeah, hopefully I didn't. We pointed to the V8 build library, and we link into V8 monolith, which implements all the methods that we need to run V8. So these are all static libraries that we're creating. Then we want one more library, which is for Python. So we point it into our local Python installation. Right, this is actually the final build, and the one that follows up below is something else. So I decided it would be very fun to run some benchmarks, and we're going to do that in closing. So we call our driving, we compile our driving runtime.c, the one that loads all the other runtimes. We compile py.c, and then we make sure we also link into Python, and we link into the JVM and we link into our local library with JS, and we link into our local library that loads the CLR. So quite involved, but again, because now we understand how to manipulate programs of this and libraries and code of this is possible. So, and we can do much more actually, probably for future versions of this talk. We probably want to create our own language, have that run besides all the other languages. But we need to make a careful decision on that. So let's compile. And we should have inside bin drive-in should be our runtime, but I actually have a dedicated script to run it because we want to tell the Python runtime not to buffer standard out for performance reasons. We need to tell it from where to look for Python packages. And remember, our Python packages is inside plugins, drive-in plugin.py. We tell the JVM, we actually tell macOS from where to look for the JVM, and we pass some arguments for our Python plugin, but this could generally be skipped. There's a better way to do this. Generally, instead of hard coding all these plugin file names, it would be better to scan at load time what to load and what not. So let's run this. Remember, every language will output its initials or its abbreviation, so py, and then it would print also the input parameter that's being called, so JS input parameter, and for Java, J input parameter, C# message. So if we run that, which is actually coming, of course, from a pointer to that memory, which we are marshalling into string. There we go. Our runtime is calling every second into the other runtimes, incrementing a counter. So quite fun, and I'm thinking that we can get creative and do some other interesting things. In closing, I'll leave you to a nice benchmark here. Please don't make conclusions, but if you can spot some interesting spikes, that would be one of the reasons to get involved into building something similar like this, or at least some strong foundations that can provide for further extensions in the future. This will be the last demo that we do for today, so please enjoy. Thank you very much for your time. I hope that this material was valuable to you, and have fun watching the rest of the sessions.